Good evening, all. So, let's start today's live discussion session for NPTEL course Soil Mechanics Geotechnical Engineering I. I'm Reshma R, Research Scholar from Civil Engineering Department, IIT Madras. I hope I'm audible to all of you. Can anyone please respond? Am I audible? All right. So, I hope everyone have gone through the lecture videos of last week. So, I'll share my screen now. Okay. Is it visible? Okay, I'll join from my phone also. 1 second. So yeah, all right. So we'll move on to the first question for today's live discussion. That is, in a constant head permeability test, water is allowed to pass through a cylindrical soil sample 20 centimeter high and 12 centimeter in diameter under a constant head of 2 meters. The water flowing out of the sample is collected in a glass cylinder of 1200 centimeter cube capacity. It is observed that the cylinder just starts to overflow after 1 hour, 30 minutes, and 30 seconds. The coefficient of permeability of the soil sample in centimeter per second is. So, here we are given a data of a constant head permeability test. So the soil sample is of height 20 centimeter and 12 centimeter diameter, and the constant head maintained throughout the test is 2 meters. So when we are collecting uh, the water that is flowing out of the sample in 1200 centimeter cube, it was found that the water is overflowing after 1 hour, 30 minutes, and 30 seconds. That is, at that particular time, it is becoming full. So, whole 1200 centimeter cube water is collected within that 1 hour, 30 minutes, 30 seconds. So, we are asked to determine the coefficient of permeability of the soil sample. So, can anyone please answer? I'll Okay, I can see the in-call messages. So, can anyone please solve it and put it in the chat box? It's just substitution a simple equation of constant head permeability test. There's a direct equation for determining coefficient of permeability using constant head permeability test. So we have two types of permeability test. That is laboratory test. We have two types. One is constant head permeability test, and the second one is falling head permeability test. So in constant head permeability test, there is one particular equation, and for falling head we have another uh, equation for determining coefficient of permeability. Should I solve, or like should I start solving, or do you need some more time to solve? I'm not seeing any answers in the chat box. All right, I'll solve it. So let's see. So the answer is A. Option A, 1.95 into 10 raised to minus 4 centimeter per second. So we'll see how. So we are given that the capacity of the glass cylinder used to collect the water flowing out of the sample, that is 1200 centimeter cube. Time of overflow is 1 hour, 30 minutes, 30 seconds, or 5430 seconds. So that is the total time required to fill that glass cylinder. Total height of the soil sample is 20 centimeter, constant head is 2 meter, and diameter of the soil sample is 12 centimeters. All these data is given. So we can calculate the cross-sectional area of the soil sample as pi by 4 d square, where d is the diameter of the soil sample. So we will get the cross-sectional area of soil sample as 113.097 centimeter square. So all these values are already given. We have just calculated the cross-sectional area of the soil sample. Right. Okay. So coefficient of permeability for constant head permeability test. The equation is K is equal to QL by HAT. Coefficient of permeability test using constant head permeability test is K is equal to QL by HAT, where Q is the capacity or the total discharge, that is 1200, into L. L is length or height of the soil sample, so that is 12. Then H is the one second, which one now data is there? Okay, sorry. L is the diameter of the soil sample, and H is the um, height of the soil sample. And then A is the cross sectional area of the soil sample. Also, time is applied in seconds, so that we'll get in the centimeter per second unit, because we are asked to find out coefficient of permeability in centimeter per second. So we have converted time in seconds, and all the other data is already in centimeters. So we'll get coefficient of permeability as 1.95 into 10 raised to minus 4 centimeter per second. Is this clear? Should I explain once again? If I'm going too fast, please slow me down. So, if this is okay, can you please put yes or okay or something in the message chat box? Should I repeat once again? It is just a direct substitution in the equation for coefficient of permeability using constant head permeability test. We usually do constant head permeability test for coarse grain soil, and we do falling head permeability test, another type of test for fine grain soil. So this particular equation we use for determining coefficient of permeability in the case of constant head permeability test. Okay, someone has raised a hand. One second. Yes, Jageshwar, please unmute and ask the doubt.
Ma'am, please repeat again.
Yeah, okay, one second. So, question was, in a constant head permeability test, that is, we are conducting a constant, we have conducted a constant head permeability test, and the soil sample is cylindrical in nature with a total height of 20 centimeter and diameter of 12 centimeter. The constant head maintained for the test was 2 meter. That's why this particular permeability test is called constant head permeability test. In the falling head permeability test, we don't keep the head as constant. So here the constant head is 2 meter. And then we are measuring the volume of water that is coming out of the sample by collecting that in a glass cylinder, and that glass cylinder will overflow at this particular time, that is at the time 1 hour 30 minute 30 second, it will overflow. That means at that point the bottle or the jar is completely filled, right? So we need to determine the coefficient of permeability of the soil sample. For that, first we are noting down all the values that is given, that is capacity of the glass cylinder, time of overflow, then height of soil sample, constant head and diameter of the soil sample, everything is already given. Then we are determining the coefficient of cross sectional area of the soil sample first. That is, we know the diameter of the soil sample. When we know the diameter, in order to determine the cross sectional area, we just have to apply pi by 4 d square, right? So here d is 12 centimeters. So calculating, we have 113.097 centimeter square, right? Now, in order to determine coefficient of permeability, we have two equations. One is for using constant head permeability test, and the other one is for falling head permeability test. So using constant head permeability test, when we do, we have the equation QL. K is equal to QL by HAT. QL by HAT. So, one second. I think I have made a mistake in writing the substitution. The answer is same 1.95, but I think I have wrongly typed it as uh, instead of L, I have made it like this. L is 20 centimeter. So I'm just changing that. Okay. Yeah. So we have Q is 1200. That is total discharge that has come out from the soil sample. Then length of the soil sample that is considered for testing, that is 20 centimeter. Then h is given constant head, that is also given 2 meters. So we are converting it into centimeters, 200. Then cross sectional area that we calculated in the earlier step, and then time in seconds. So when we substitute, we'll get it as 1.95 into 10 raised to minus 4 centimeter per second. Is that clear?
Yes, ma'am.
Okay. So we'll move on to the next question. Match list 1 with list 2. In the list 1, we have certain types of rollers, and in list 2, we have certain types of soils. So which kind of roller do we use in which kind of soil? So can anyone put the answer in the chat box? It's just a match the following type of question. Where do we use a pneumatic roller, a smooth wheeled roller, sheep foot roller, and vibratory roller? Any answer? Okay, I have got one answer. Yes. All right. Okay, see, we'll see. Okay, one answer I've got is option C. Okay, we'll look what is the correct answer. Yes, answer is C. That means pneumatic roller is used for silty soils with low plasticity kind of. Smooth wheeled kind of roller is for cohesive and granular soils. Sheep foot roller for plastic soils with moderate cohesion. And vibratory rollers are used for cohesionless soils. So this is there in the lecture videos as well, in the downloadable notes as well. Okay. So we'll move on to the next question. In a compaction test with increase in compactive effort, option A, both maximum dry density and optimum moisture content increases. Option B, both maximum dry density and optimum moisture content decreases. Option C, maximum dry density increases, optimum moisture content decreases. Option D, maximum dry density decreases and optimum moisture content increases. Which one is the correct option? What is the change that will happen to maximum dry density and optimum moisture content when we increase the compactive effort? Anyone? We have a graph connecting um, this compactive effort, maximum dry density, and the moisture content. I have got one answer as option B. Any other answers?
Option C.
Okay, so we'll look what is the correct answer. Yes, option C is the right answer. So, in a compaction test, when we increase the compactive effort, maximum dry density increases, but optimum moisture content decreases. So, if we look into this graph, we can see that when with the increase in number of blows, increase in compactive effort means we are increasing the effort applied or the force applied, right? So when the number of blows are increased, the optimum moisture content is shifting to this side. That means optimum moisture content is decreasing, whereas dry unit weight is getting lifted up. That means maximum dry density is increasing. Is that clear? All right, here is our next question. Ma'am, I can't get the answer. Which one? Which answer? Um, I'm not. Anadi Barik. I guess that is the pronunciation. So, which answer you are not getting? Can you please unmute and tell me, or can you please type it on the chat box? Which answer do I need to explain once again, or can you specify the question number? Is it the previous question? 20CV041. Are you there? Okay, I think he's not here. Okay, we'll move on to the next question. A concrete weir is founded in okay, previous question. Okay, okay, all right. So this question, in a compaction test, the question asked is when we increase the compactive effort. That is when we increase the effort that is applied for compacting or force that is applied for compacting. What will happen to dry density, maximum dry density, and optimum moisture content? Right. So we have a graph that we plot after doing this compaction test between dry density and moisture content. And there we get the maximum dry density and the corresponding moisture content as optimum moisture content. So the option, okay, you are having network issue. It's okay. So the option, correct option is option C. That is maximum dry density increases and optimum moisture content decreases. That is, if we see this graph, you can see that when we increase the number of blows, that is what we mean by increasing the compactive effort, right? The optimum moisture content point is shifting to this side. That is, it is decreasing, whereas the dry density is raised up. That means it is increasing. So the maximum dry density increases and optimum moisture content decreases when we increase the compactive effort. Is that clear now?
Yes, ma'am.
So next question is, a concrete weir is founded in an anisotropic soil mass. The coefficient of permeability in the horizontal and vertical directions are respectively 4 into 10 raised to minus 4 mm per second and 1 into 10 raised to minus 4 mm per second. The equivalent coefficient of permeability of the soil mass in mm per second is. So we are given Kh and Kv, that is coefficient of permeability in the horizontal and vertical direction, and we are asked to determine the equivalent coefficient of permeability. There is a single equation for that, connecting equivalent coefficient of permeability and coefficient of permeability in horizontal direction as well as vertical direction. So I have got one answer, that is option A. Any other answer? I think even without a calculator you can solve that. If you know the equation, it's very easy just to substitute because the values are also like that. Any other answers? One answer I have got is option A. Any other? Okay, let's see. So the answer is option A. So it's given that coefficient of permeability in the horizontal direction is 4 into 10 raised to minus 4 mm per second, and in vertical direction is 1 into 10 raised to minus 4 mm per second. Then equivalent coefficient of permeability is square root of kx ky. That is square root of 4 into 10 raised to minus 4 into 1 into 10 raised to minus 4, which is equal to 2 into 10 raised to minus 4 mm per second. So it's the square root of kx ky. Kx is in the horizontal direction, ky is for vertical direction. I'll pause here for a moment. If any doubts regarding the last four questions, please do ask. Either you can raise your hand or you can unmute and ask the question, or you can type it in the chat box if you have any doubts. If not, we'll move on to the next question. Okay. So here is the next question. The number of flow channels and head drops is 3 and 6 respectively in a flow net. The difference in the upstream and downstream water level is 5 meter. If K is equal to zero point 0.2 meter per second, the quantity of seepage per meter width of a sheet pile wall is. So the number of flow channels and head drops is 3 and 6. So NF, number of flow channels NF is equal to 3. Number of head drops ND is equal to 6. We are also given the difference in the upstream and downstream water level as 5 meter. Coefficient of permeability K is given as zero point 0.2 meter per second. We are asked to determine quantity of seepage per meter width of a sheet pile wall. So I've got one answer, option A. So we'll see what is the answer. It's option A. So it's given number of flow channels is 3, number of head drops is 6, difference in upstream and downstream water level is 5 meter, and coefficient of permeability is zero point 0.2 meter per second. Now the equation for quantity of seepage per meter width of sheet pile wall is KH into NF by ND, where K is the coefficient of permeability, H is the difference in upstream and downstream water level, NF is number of flow channels, and ND is number of head drops. Substituting, we get zero point 0.5 meter cube per second, that is option A. Is that clear? It's just a straightforward equation. Q is equal to KH into NF by ND. Okay. So here is our next question. A sand deposit has a porosity of zero point 0.5. So small letter n is equal to zero point 0.5. And its specific gravity, capital G, is 2.67. The critical hydraulic gradient for the sand deposit is. So porosity n is equal to zero point 0.5. Specific gravity G is equal to 2.67. Then critical hydraulic gradient IC for the sand deposit is. We have an equation for IC connecting G and E, but we don't have void ratio E. We are given porosity N. but we know how to calculate porosity. I mean, how to calculate void ratio from porosity. So, okay, I have got one answer, that is option D. Anyone else? I'll wait for a few minutes, like 1 minute, then I'll show how to solve the problem. Okay, let's see how to solve. So, option is D. Correct option is D. So, what is given? We are given porosity and specific gravity. But we know critical hydraulic gradient is given by the equation G minus 1 by 1 plus E. That means we need void ratio E. We know that void ratio E is equal to N by 1 minus N. N is given, porosity N is given. So we have E is equal to zero point 0.5 by 1 minus zero point 0.5, which is equal to 1. Therefore, critical hydraulic gradient IC is equal to G minus 1 by 1 plus E. That is 2.67 minus 1 by 1 plus 1, which is equal to 0.835. Any doubts? Alright. So we'll move on to the next question. That is, the subsoil at a site consists of a fine sand layer lying between a clay layer at top and a silt layer at bottom. So we have a three-layered soil. At the bottom silt, above that fine sand, above that clay. The coefficient of permeability of the sand is 100 times that of clay and 50 times that of silt. So, and also the thickness of each layer is same and equal to capital H. So we have three layered soil, each layer having equal height capital H. But their coefficient of permeability is different, such that the coefficient of permeability of the middle layer, that is the sand layer, is 100 times that of the clay layer and 50 times that of the silt layer. Then the ratio of equivalent coefficient of permeability of the deposit in directions parallel and perpendicular to bedding planes. That is, we are asked to find out Kh by Kv, ratio of equivalent coefficient of permeability of the deposit in parallel and perpendicular directions. So I'll wait for 2 minutes. Can anyone solve and put it in the chat box? We have four options here. So first we need to find out what is the coefficient of permeability in the parallel direction and then in the perpendicular direction, and then take the ratio. We are given the height and coefficient, individual coefficient of permeabilities in terms of H and some ratios. Any answer?
Option D.
Um, Option D, I don't think that is a correct answer. Any other answer?
14.25.
Sorry?
14.25.
Mm, okay, let's see. Any other answer? Anyone?
34.33.
Okay, so I got option A and option D. Any other answers? All right, so we'll see what is the correct answer. Correct answer is option B. So what we have is a type of soil like this: clay here, sand here, and silt here. So we are given that coefficient of permeability of sand is 100 times that of clay and 50 times that of silt, right? So if we take the coefficient of permeability of clay as K, coefficient of permeability of sand will be 100K, right? But that is also equal to 50 times that of silt. That means coefficient of permeability of silt is 1 by 50 times that of sand. That means 1 by 50 into 100K or 2K. Already thickness they have given as capital H. Is that clear till this point how I have took the coefficient of permeability for each layer from what it is mentioned in the question?
Yes, ma'am.
Okay. Should I repeat it once again?
Yeah, ma'am, you can repeat.
Okay, so coefficient of permeability of the clay, we are assuming it as K. Already they have given the coefficient of permeability of sand is 100 times that of clay. So we can write it as 100K. Another relation that they have given is coefficient of permeability of sand is 50 times that of silt. Or we can write it as coefficient of permeability of silt is 1 by 50 times of sand. That means K, 100K and 2K are the coefficient of permeabilities of each layer. Now, we have two separate equations for the equivalent coefficient of permeability for the parallel plane and perpendicular plane. First, considering the perpendicular bedding plane, we have the equation Kv is equal to sigma hi by sigma hi by Ki. H is the depth of the layer and K is the coefficient of permeability of that layer. So here all the depths are same, that is capital H. First layer has a permeability K, second has a permeability 100K, third one has a permeability 2K. So calculating, here we can take H by K outside as common. Remaining here 1 will be there, here 1 by 100 and 1 by 2. So substituting and H gets cancelled. This K from the denominator, it will go to numerator. So we will get as 300K by 151. This is the average coefficient of permeability or equivalent coefficient of permeability perpendicular to the bedding plane. Right. Now, parallel to the bedding plane, our equation is sigma Ki by sigma Hi. Substituting, we have Hk plus H into 100K plus H into 2K by 3H. So H and H again gets cancelled. It becomes 103K by 3. Now, we need to take the ratio of horizontal to vertical, that is KH by KV. We get 17.281, that is option B. Option B is the correct answer. Is that clear?
Yes, ma'am.
So shall we move on to the next question? So here is the eighth question. A pumping soil test was made in pervious gravels and sands extending to a depth of 16 meter where bed of clay was encountered. So we are conducting a pumping soil test up to a depth of 16 meter and the normal groundwater level was at the ground surface. So from the ground surface we went till 16 meter for conducting a pumping test and the normal groundwater level is at the ground surface. We have two observation wells. One is located at a distance of 3 meter and the another one is located at a distance of 7 meter from the pumping well. At a discharge of 30 meter cube per minute from the pumping well, a steady state was attained in about 24 hours. The drawdown in observation wells at a distance of 3 meter was 2 meters and at 7 meter was 0.75 meters. We are asked to determine hydraulic conductivity of the sand. So there's a direct equation and it is a direct substitution only in this question. All the data are given, we have to substitute in the equation for hydraulic conductivity using pumping test. We are given two observation wells whose distance are one is 3 meter away from the pumping well, another one is 7 meter away from the pumping well. When we take out a discharge of 30 meter cube per minute from the pumping well, a drawdown of 2 meter is found in the first well, that is the well at 3 meter distance, and a drawdown of 0.75 meters found in the second well. Okay, one answer I have got is option A. Any other answers? Okay, we'll see. So the correct option is option D. So we are given that distance of the observation well from the pumping well R1 and R2. They are given as 3 meter and 7 meters. Discharge from the pumping well is given as 0.5 meter cube per second. Normal groundwater level is at 16 meter ground level. So the height of the bottom point to the ground level is 16 meters. Drawdown in observation wells is one is 2 meter and the other one is 0.75 meter. The thing we have to note here is the value given is drawdown S1 and S2. But in the equation we have H1 and H2. That is, we need to deduct it from the actual height. So hydraulic conductivity of the sand for pumping test, the equation is Q ln R2 by R1 by pi into H2 square minus H1 square, where H2 is equal to capital H minus S2 and H1 is equal to capital H minus S1. So we get 14 and 15.25 respectively for H1 and H2. Then hydraulic conductivity, when we substitute all the values, it becomes 3.68 into 10 raised to minus 4 meter per second. I hope that is option B. Yeah, 3.68 into 10 raised to minus 3. Somewhat. Yeah, that's 3.68 into 10 raised to minus 4. That is option B. So it's a direct substitution. Only thing you have to note down is in the equation it is H2 and H1, which we get by deducting the total H from the, drawdown from the total height. The value given in the question is drawdown, but we need to determine the opposite value, like the deducted value. Is that clear? Rest is like direct substitution only in the question. All the other values are given directly in the question. Okay, so we'll move on to the next question. Okay, so in the initial one question, we saw constant head permeability test. So in this question, we have falling head permeability test that is being performed on a soil specimen of diameter 8 centimeter and height 12 centimeter. So specimen diameter is 8 centimeter. Now we have stand pipe of diameter 1.1 centimeter and the water level is dropping from 60 to 45 centimeters in 2 hours. The time required for the water level in the stand pipe to come down to 32 centimeter is. So initially when we conducted the test, the water level is dropping from 60 centimeter to 45 centimeter and that is happening in 2 hours. So the question is, what will be the time required for the water level to drop from 60 to 32 centimeters? Q value. In which question? Is in the previous question, Sampath? Q value is directly given in the previous question, that is 30 meter cube per minute. But it is in minute. Meter cube per, we have to convert that into second. because we have here given it in the meter cube per minute option. So when we convert that into meter cube per second, it becomes 0.5. Okay. All right. So in this question, we are given falling head permeability test, and we are already given that in the first case, the water has dropped from 60 to 45 centimeter in 2 hours. What will be the time required for the water level in the standpipe to come down to 32 centimeters? The question. Any answers? We are given two separate cases. From one case, we can determine the coefficient of permeability, and by substituting that in the second case, we can determine the time required for the water level to come down to 32 centimeters. I'm not seeing any answers here, so okay, I'm not seeing any answers in the chat box, so I'll explain how to do this. So the correct option is option A, that is 4 hours and 22.2 minutes. So let's see how to solve. So here we are given the data of soil specimen, that is diameter as 8 centimeter and height as 12 centimeter. Also the diameter of the standpipe is 1.1 centimeter. In the first case, the water level is dropping from 60 centimeter to 45 centimeter in 2 hours. In the second case, water level is dropping from 60 centimeter to 32 centimeter. Sorry, the time here is unknown. So the water level is dropping from 60 centimeter to 32 centimeter. The question is, what is the time of drop? So cross-sectional area of soil specimen is pi by 4 into 8 square, and cross-sectional area of standpipe is pi by 4 into 1.1 square. For falling head permeability test, the coefficient of permeability equation is AL by AT1 into ln H1 by H2. Small letter a in the numerator is cross-sectional area of standpipe, and the capital A in the denominator is cross-sectional area of the soil specimen. So, when we substitute this for the case 1, we have K is equal to pi by 4 into 1.1 into 1.1 into 12 by pi by 4 into 8 into 8 into 2, that is in hours, we are converted into seconds, so 2 into 60 into 60 ln 60 by 45. Since pi by 4 are getting cancelled, I have not mentioned that in the equation. So from this we'll get K as 9.065 into 10 raised to minus 6 centimeter per second for this particular soil sample. Right. Now, if we consider the second case, there we have all the other values except T. So from this equation for coefficient of permeability, if we resubstitute or rearrange for T1 or say T2, we get the time as 1.1 into 1.1 into 12 divided by that K we should substitute from the earlier obtained value. And since the options are given in hours and minutes, we have to convert this obtained value, that is in seconds, to hours and minutes by dividing by 60. Is that clear? Okay, there are no response. Okay, so I think it's clear. So we'll move on to the last question. The flow net around a sheet pile wall is shown in the sketch. The properties of the soil are permeability coefficient is 0.07 meters per day, Isotropic. Specific gravity is 2.67 and void ratio is zero point 0.9. The sheet pile wall and the bottom of the soil are impermeable. The seepage loss in meter cube per day per unit length of the wall of water is. We are asked to assume number of flow channels as 4. So same equation we had applied in one of the previous questions, that is Q is equal to KH into NF by ND. Here also we are given the values of K, then H we can determine from the figure. NF is given 4, we can assume it as 4, and ND. ND is number of drops. So let's see how to solve. So the correct option is option B, 0.29. So we are given number of flow channels as 4, number of head drops as 8, and difference in upstream and downstream water level, that is given in the figure actually. It is not mentioned in the um, question. So we have to deduct that upstream and downstream water level. So we get 10 minus 1.5, which is equal to 8.5. So coefficient of permeability is also given as 0.07 meter per second. So applying the same equation, KHNF by NB, we have 0.07 into 8.5 into 4 by 8, which is equal to 0.29 meter cube per second. So any doubts? Okay, I'll stop the screen sharing. One second. Okay. So if you have any doubts, either please raise your hand or unmute yourself, or you can put the question in the chat box also. Okay, so if there are no other doubts, then we can conclude for today, and we'll meet during the next live discussion on next Monday, 6 p.m. All right, thank you all.